What do this satellite thruster, plastic tool, and micromechanical switch have in common? Well, they all contain components that bend, so-called compliant mechanisms. This episode was sponsored by SimpliSafe. More about them at the end of the show. Now, about a month ago, I was giving a talk in Utah, hence the suit. And that's where I met this guy.
Larry Howell, professor of mechanical engineering. So it's always been considered to be bad to have flexibility in your machines. Well, we've tried to take that thing that everybody hates and is trying to avoid and say, how can we use flexibility to our advantage? How can we use that to do cool stuff?
Now, Professor Howell literally wrote the book on compliant mechanisms.
That's the most cited book.
But he's pretty nonchalant about his work. Just watch how he introduces this mechanism he developed to prevent nuclear weapons from going off accidentally.
Actually, it's safing an army of nuclear weapons. And so
What?
if you want to
Hang on. What are nuclear weapons?
safing an army. So,
Safing and arming.
Yeah, so if there's anything in the world that you want to be safe that is not going to accidentally go off.
I feel like it doesn't even need saying, but yes, nuclear weapons, obviously you don't want them to go off. Well, I don't understand how this is going to keep nuclear weapons safe. Now, I want to come back to this device and explain how it works, once we understand why compliant mechanisms are best suited to this task.
That's cool.
So let's start with something basic.
Probably the first compliant mechanism I ever designed was this thing. What it is a compliant mechanism that is a gripper. So you can put something in there and it'll get actually a really high force. I can put that in there and it breaks the chalk.
What if you put your finger in there and squeeze it?
You would scream in pain. Would you like to try?
I would.
Okay.
Like I would actually like to feel the force.
Okay. You need to squeeze it yourself though. Or
Really?
Well, all right. I'll squeeze till
But,
you
like,
scream in pain.
don't. Ah! That very quickly got incredibly painful. It felt like having my finger like in a vice.
That looks suspiciously like vice grips, but now with these flexible components where the hinges are.
What I learned in my visit with Professor Howell is that compliant mechanisms have a number of advantages over traditional mechanisms. But I thought he needed kind of a clever, pithy way to remember all of these advantages. So I came up with the 8 P's of compliant mechanisms. And the first of those is part count. Compliant mechanisms have reduced part count because they have these bendy parts instead of having things like hinges and bearings and separate springs. This gripper is just a single piece of plastic, but achieves a similar result to the much more complicated vice grips.
Like how much does it amplify the force?
This will get about 30 to 1. So I can get, for 1 pound force in, get 30 pounds out. So
That's pretty good.
Yeah.
Seems like that would be super cheap.
and really inexpensive. So this we just made here in our shop, but you can imagine also injection molding that.
That would cost like cents.
Yep, this would cost cents. The other thing is, because of its shape, you could extrude it and then just chop them off. That would be cool.
So the simple design allows different production processes to be used, which lowers the price. These switches, for example, achieve in one piece of plastic what is normally done with springs, hinges, and many rigid plastic pieces.
Also a good fidget device.
How long can these last?
We've had these in our fatigue testing machine. We've been able to go over 1 million cycles without failure.
What do we got there?
All right, Derek, I've got a quiz.
Uh-oh.
A quiz for you. Okay?
Elephant.
Very good. Okay, I'm gonna push on the elephant's rump this direction. Okay, I'm gonna hold this, and that little dot right there is that dot. When I push on it, is it gonna go left, right, up, or down?
I just, you know what? I wanted to guess without even thinking about it.
Please do.
I'm gonna say like up and in.
Okay, up
And
and
I kind of feel like that because like that would be a logical way for an elephant to hold its trunk
okay,
more than.
sure,
But also
good
because
point.
like if this is all going over, I feel like this is gonna kind of extend there, and that's gonna get pushed up in there.
Good thinking.
Well,
Excellent.
I don't know. Is that good thinking?
It's thinking at least. So this is designed so that when you push on that, it actually just rotates in space. It doesn't move at all.
I knew you were gonna pull some sort of trick
It's a trick
on me.
question.
Now, since I was fooled by it, I had to try it out on my friend, the physics girl.
That's so trippy. That is so cool. I don't understand. What?
It's modeled after the mechanisms you use in wind tunnels, where you want to have, say, a model that's attached here, but then you move it, and all you want to do is control its angle and not move it around in the wind tunnel.
Don't
And so-
displace it, but
Yeah.
but be able to change the angle.
Devices like this demonstrate that compliant mechanisms are capable of producing very precise motion, which I personally found pretty counterintuitive because these objects are made up of flexible parts. But maybe that shouldn't be surprising, because compliant mechanisms don't suffer from backlash, for one thing. So backlash occurs when you have a hinge, which is basically just a pin in a hole, and it's moving in one direction. And now, if at some point the motion reverses, it doesn't happen instantaneously because there's some give in the hinge. This also causes wear and requires lubricant, and that is why compliant mechanisms have better performance than their traditional counterparts.
This one, though, is my favorite.
That is one of my favorites too. It's just so pleasing. Right?
Oh, that sound is so satisfying.
This actually, believe it or not, was inspired when we were doing things at the microscopic level, where we're building compliant mechanisms on chips. We had to be able to make these compliant mechanisms out of silicon, which is as brittle as glass. And if you're trying to make something like this out of glass, right, it's crazy hard. But that also means once we figured out the design, we could make it in a material even like PLA, which is also, not the ideal compliant mechanism material. So you can get on our website and get the material and get the files to make this yourself.
I'll put a link in the description.
Yeah, that also has a nice feel and a nice snap to
It
it.
has a really nice snap. I like when it comes out, it's like gunk. Like there's something about that that's really, it's very pleasing.
So these things actually move?
Oh yeah, yeah, yeah.
I need to
Sure,
see this.
Okay, all right, we'll do it.
Were those etched on there?
Those are etched, and so just using the same processes used to make computer chips.
So another advantage of compliant mechanisms is that they can be made with significantly smaller proportions because they take advantage of production processes like photolithography.
And we have motion that we want at the microscopic level.
That's brilliant.
Plus, since they simplify design, compliant mechanisms are much more portable, meaning lightweight, which makes them perfect for space applications.
This here is something we did with NASA, making a hinge that could replace bearings for, say, deploying solar panels. This is titanium, 3D printed titanium. But what's freaky about it is you get that motion, which people expect, but there's a piece of titanium that can bend plus or minus 90 degrees, 180 degree deflection.
That is solid titanium.
That is one piece of titanium that is 3D printed.
There's no alloy, nothing to make it flexible.
Yep, this is, and even freakier than this is this guy right there. So that looks like a crazy beast, but every part in there has a purpose. All these flexible beams, here are the two inputs. And again, we did this with NASA for a thruster application, where we can put a thruster right there, and now with our two motor inputs we can direct that thruster in any direction. That titanium device moves out, and you notice that it's just all bending, and then there's no pinch points for the fuel lines or electrical lines coming in.
Here, this single piece of titanium allows you to use one thruster in place of two. Okay, that is a clutch.
Okay.
So the idea is, if you spin it up really fast, because it's flexible, this outer part will actually start coming outwards. And then if there's a drum around it, it'll contact with that drum and spin that thing.
Oh, so this that kind of comes out like so,
When
and
it
then
gets spinning really fast, and then you essentially engage this outer drum. So this is like the way that a
Wow.
chainsaw would work or something like that, because you get it spinning fast enough, and then it engages the chain, and then it turns it over, and then
force. Yeah. Wow, that's cool.
So here, this is made in plastic so that it, you can see it, but in reality, it's got to be a lot stiffer. So here it is, made in steel.
What? So hang on, you're saying that thing, which is made of steel,
Yep.
you spin it up to a certain speed, and then it expands and engages a drum that's
Yep.
around it.
Yep. So it will idle with no motion, but then at a certain speed, that are what we designed it for, it'll speed up to that RPM.
You speed it up and it engages.
Yep.
I had no idea. Like, I have learned something today.
So let's come back to the safing and arming device for nuclear weapons. Its purpose is to ensure that no random vibrations, say from an earthquake, inadvertently disable safeties and arm the nuclear weapon. Now, one of the requirements was that this device be made as small as possible.
They had made those as small as they possibly could using traditional methods, even using things like what the Swiss watch manufacturers were using.
With compliant mechanisms, they produced a device out of hardened stainless steel, where some components were the size of a human hair. This is high-speed video. Here the device is operating at 72 Hertz, meaning this little hole makes 2 complete revolutions each second. The way it's meant to work is an arming laser shines on the rotor wheel, and when the proper input is given to the system, the wheel rotates a notch. If all the proper inputs are given, then the hole lines up with the laser beam, and crazy things happen from there. So it is essential that this device's performance is perfectly predictable, even if it sits unused in a silo for decades.
So, are these now being used on nuclear weapons?
You know, it turns out they don't tell us what they do with their nuclear weapons. And so we designed them, we made prototypes, we tested them, and then it goes what they call behind the fence, and where it's all classified, and you know, we don't know what happens. So.
Hey, this episode was supported by viewers like you on Patreon and by SimpliSafe, incredibly effective, reliable home security. Now, I started thinking seriously about home security one day when there was this police helicopter circling overhead, and it turned out that the house across the street had been broken into. SimpliSafe makes it easy to protect your home. They sent me a kit, including a base station, camera, and multiple sensors, and the setup was simple. It only took me about an hour to complete. The system is monitored by professionals 24/7, and they can call you or send police in the event of a break-in. So it's easy and intuitive to use. There's also these thoughtful features that are built in. For example, it reminds you if you left the door open. Pricing is fair and honest with no contracts or hidden fees, and it's equipped for worst case scenarios, like if the Wi-Fi goes down or the power is out, it still works. So to find out more, go to simplisafe.com/Veritasium. I want to thank SimpliSafe for supporting Veritasium, and I want to thank you for watching.